So maximum power transfer. Maximizing the amount of power transferred from a power source to a load is important, and it's a major focus area in systems design. The power not transferred to the load for useful work is usually wasted. So wasted power goes to generating heat, in which case the system cost will certainly increase. In many cases, the system cost will certainly increase due to the addition of cooling solution. Because when we have additional heat, that means we have to provide cooling to ensure that the system remains balanced and it continues to work effectively. In mobile systems, batteries get depleted faster if excessive power is wasted. For some of you who may have noticed when you use your phones or your computers or your other mobile devices, you find out that when excessive power is wasted, your battery gets depleted or used up on time. In communications, the load needs to receive more minimum amount of power before the link is healthy. Okay, so healthy link would mean that before the voice is clear, before the image is clear, and so on and so forth. So in power quality systems, the electric power loss in generation, transmission, and distribution becomes very significant if efficiency is low due to large amount of power. So let's quickly look at what is going on here. There is a question here we can easily look at together to understand what maximum power transfer condition is and how we can easily represent it in our work. Determine the value of the resistance in the following circuit in order to transfer maximum power from the source side to the load side. So this is the source side and this is the load side. And then this is the given circuit here. So the first thing you want to do is to simplify the circuit to its Thevenin equivalent form. Okay, we have talked about Thevenin equivalent circuit, Norton equivalent circuit, and all of those right from the previous classes, previous sessions we had. If you have not checked those videos or those lessons, check them. They are, on the platform. So when you convert this circuit to its Thevenin equivalent, this is exactly what you're going to have. So you can see we have R equivalent. You can see we have the load resistance here, and then from here we can then go ahead and observe two cases. We have the first case when the resistance is short-circuited. In that particular case, it simply means RL is 0. When the resistance is short-circuited, it simply means that there is no resistance at all. It simply means that there is no hindrance, no load resistance at all. All right? And that would mean it allows maximum current to pass through when we have a short circuit. It allows a maximum amount of current possible to pass through. Okay, so the load power would be 0 in this particular case. Look at how that happens. We have power equals RL multiplied by I squared. This is the usual formula for power that we are familiar with. And we know our I is V equivalent over R equivalent plus the load resistance, which of course is 0. So it would be V equivalent divided by R equivalent, all multiplied by 0 because RL is 0 at this point. So the power will be equal to 0 at the end of the day. This is the first case when we have resistance short-circuited, meaning that RL is equal to 0. The second case is when we have excessive resistance, when we have a very large load resistance. Okay, in that particular case, we can represent the load resistance with infinity. It is infinitely large. That's what that means. At the end of the day, again, the power would be equal to 0, and this is how that happens. We can say our P is equal to Ri squared, where in this case, our R is equal to infinity, or RL is equal to infinity. So infinity multiplied by V equivalent divided by infinity plus R equivalent. Okay, infinity plus R equivalent certainly would still be infinity. V equivalent divided by infinity would therefore be equal to 0. The inverse of infinity is equal to 0. Okay, from your mathematics, you should know that. So if we have V equivalent divided by infinity to be equal to 0, that simply means we have 0 squared multiplied by infinity. 0 squared, of course, is 0. So 0 multiplied by infinity will definitely give us 0. So in any case, case 1 and case 2, when we short circuit the resistance or open the circuit for resistance, it simply means that our power would be equal to 0. Okay? So let's look at this mathematical fact. A function passing through 0 at 2 distinct points possesses at least one extremum point between these points. An extremum point would be the maximum point or the minimum point. Okay, so that point is usually the peak or the crest of that particular curve or that particular graph. In this particular case, these are 2 distinct points on the graph. All right, you can see we have these 2 distinct points. Between these 2 points, there has to be a maximum point or a minimum point or an extremum point. Okay, so this extremum point is what we have right up here. It must have that point one way or another. Okay. So this equation is one of the most important equations you have to pay attention to. P equal to RL I squared, which is going to be equal to RL multiplied by V equivalent over R equivalent plus RL, all brackets squared. Okay, so this is going to be the expression you use to find our power, all right? And then the optimum value of RL, if you look at this particular curve, the optimum value of RL will be when we have the highest point on the graph. Okay, at that point, our RL is 5 ohms for this particular analysis and example. And then you notice that the maximum power drawn is also traced to somewhere as 5 watts, somewhere here. This is how to analyze such a graph. You can see we have a maximum power and then the optimum value of RL is 5 ohms here. That is why you can see we have R equivalent is equal to 5 ohms. We can see V equivalent is equal to 10 volts here today. Assume the below model where the Thevenin voltage source and the resistor on the left is the equivalent of a more complex circuit delivering power to the resistive load represented by RL. How should we design the load, that is the RL, in order to maximize the power delivered to it? Okay, how do we design the load to maximize the power delivered to that particular load? So look at this particular example or this circuit. We have our R Thevenin or R equivalent here. We have our load resistance here, and then we have the voltage source of V Thevenin somewhere here. If we want to deliver maximum power to RL, how do we make that happen? Let's quickly check it out together. We know that our P is equal to I squared R. So PL, or power delivered to the load, will be equal to current passing through the load squared multiplied by the load resistance. This will be equal to V Thevenin squared divided by R Thevenin plus RL multiplied by RL. The RL you see here, this RL you see here is the same RL we have here. Okay, and then we do know that our IL, current passing through this resistance, is going to be called IL. The current passing through the load resistance will be called IL. Since the voltage in the circuit is V Thevenin and then we have RL here, our IL will be equal to the voltage. You know from Ohm's law, right? You know from Ohm's law that I is equal to V over R. So our R in this case will be R Thevenin plus this RL. So our I will be equal to V Thevenin divided by R Thevenin plus RL. If you bring that here, you're going to have V Thevenin squared divided by R Thevenin plus RL, all brackets squared. And then you multiply that by this RL that is already here, and that gives us our power delivered to the load. Now, to find the RL that gives maximum power, this is what we are going to do. You will differentiate it. For some of us who are familiar with optimization, for some of us who are familiar with optimization, you find out that to find maximum power, the first thing you do is you differentiate your power equation and you equate it to 0. Okay, that way you will be able to find the value of a variable that will give you a maximum value. In this case, if you differentiate PL equal to Thevenin squared RL divided by this denominator, what we will have is the PL, the RL equal to, if you keep RL constant and then you differentiate this, V Thevenin squared, V squared Thevenin. I shouldn't be telling you how to differentiate, by the way. You should know that. But what is happening here is you keep RL constant and then you differentiate what we have. So RL is kept here constant. You differentiate this, you can see we have what we have here. So that gives us minus 2V squared Thevenin RL over R Thevenin plus RL cubed. And then plus, the next thing you do is you keep, in the first case, we kept just RL constant. In the second case, we're going to keep this constant. We're going to keep V squared Thevenin over R Thevenin plus RL squared constant. So that is exactly what you have here. You keep it constant and then you differentiate your RL. Your RL, when you differentiate it, you're going to have 1 because it's a variable that we have. So it's like saying when you differentiate X, what does it give you? When you differentiate X, you have 1. So when you differentiate RL, you have 1. Multiplied by this, you have this. So this is exactly what you would have when you differentiate the power equation, and then we can go ahead and equate it to 0 to find the maximum value of the variable of interest. When you do that, this is what you're going to have. V Thevenin squared in the bracket R Thevenin plus RL minus 2RL. All right. So both of them would be equated to 0. So you have this here, and then you have this here. So it's either this equals 0 or this is equal to 0. But we do know that V Thevenin cannot be equal to 0. So R Thevenin plus RL minus 2RL would be equated to 0. If you do that, what you find out is that RL is equal to R Thevenin. Okay, what this tells us is that to deliver maximum power to the load, we have to make our RL to be equal to R Thevenin. This is what this tells us. And then to confirm RL is equal to R Thevenin, to confirm that that is actually going to be the maximum that we can obtain. For some of us who are familiar with optimization, again, you would remember that you find the second derivative of our power equation or the equation in question, okay, and then you obtain a value. That value will either be greater than 0 or less than 0. If the value is greater than 0, it simply means we have a minimum point. If it is lesser than 0, it means we have a maximum point, okay? So if you find the second derivative of what we already differentiated here, what you have is this. The squared PL, the RL squared would be equal to, you are finding the second derivative of this. This is what it will give us, 6 V Thevenin squared RL over R Thevenin plus RL raised to the power 4 minus 4 Thevenin squared divided by R Thevenin plus RL cubed. And then whatever you obtain here has to be less than 0 for you to obtain a maximum value. Check out what would happen. Replace R Thevenin with RL everywhere. Everywhere you see R Thevenin, just put RL there. Whatever we obtain has to be less than 0 at the end of the day. That is how to obtain our maximum point. We've talked about this already. For maximum power delivery, our RL must be equal to R Thevenin. To maximize power delivery, the load resistance needs to be matched with effective source resistance. We've talked about all of this. Let's say we have a circuit with certain variables. Those variables can actually be either current or voltages or probably a couple of other variables. And then let's say the circuit also has linear scaling parameters such as AIs, where I could represent iteration numbers like 1, 2, 3, 4, 5 to the maximum number that we can have, amount of numbers that we can have, or series of numbers that we can have. And most certainly that would be coefficients of the variable, or the coefficients of currents and voltages as the variables we have in the circuit. In many cases, those would be constants. The A's would be constants in many cases. And then we also have a net source value called YA, the net source value of YA. Okay, and that source value could be current source, it could be voltage source. KCL or KVL can be applied to such a circuit. And when that happens, it results into this kind of an equation. This is like a linear algebraic equation. So you can see we have A1, X1, where this A1 represents constant, this X represents our variable, and this A at the top here tells us that we are dealing with a particular situation. I'm going to explain that in a couple of minutes. Okay, and then we have A2, X2 plus A3, X3 plus A4, X4, and that can continue until we get to the last term that should be dealt with. When you add all of this together, it should give us the source value. It should give us a source value. When you apply either KCL or KVL, this is the kind of equation that we are going to end up with. Now, if we go ahead and add another source, let's say we now have another source called YB, which could either be current or voltage. The first source, YA, could also be current or voltage. The second source could also be current or voltage. So there could be two currents, there could be two voltages, there could be one current and one voltage, irrespective of how it is mixed. Okay, so let's say we have a second source or another source added called YB to the circuit. And we carry out KCL and KVL analysis on the circuit. We're going to come up with another equation like the first one, but this time around, we are dealing with B, representing the fact that this equation is as a result of the new source that has been added to the circuit. Okay, the only thing that would remain constant will be A1. A1 would be the same for both equations, but this time around, the x's would have changed. So we have x1b here, not x1 here as we had in the first place. And it goes on, and at the end of the day, we equate it to YB because this is the new source that is giving us this kind of response in the circuit. Okay, so at the end of the day, superposition principle tells us that if the two sources are applied together in the circuit, the response to the new circuit is going to be the summation of the individual responses that we have. This can be referred to as first response, equation 1. This can be referred to as second response, equation 2. Addition of these two equations certainly will give us the total response in the circuit. And that will be A1, X1A plus X1B plus A2, X2A plus X2B plus A3, X3A plus X3B, and it continues on to the last term. And it will be equal to YA plus YB, the summation of the sources that we have. We can then go and say from here that the principle of superposition states that the overall response of a circuit containing several sources is the sum of the responses to each individual source with the other sources killed. So you have two sources, you kill one source, get a response. Okay, and then you document your response in form of an equation. All right, and then you go ahead, restore the source you killed, and then kill the other source, the second source, get a response based on the second source that is now alive. Okay, and then you document that as another equation. Addition of those two equations or those responses together gives us the total response of those circuit when the two sources are in the circuit. Okay, Now we have something we can briefly use as illustration. The process is straightforward and simple. In this case, we have three sources in the circuit. In this particular example, or this particular illustration, kill all the sources except one. That's the first thing you do. Then solve the resulting circuit. That's the second thing you do. Restore back the source you killed. That's the third thing you do. Kill another source in the circuit. Then repeat the procedure for all sources remaining in the circuit. Sum up all the solutions you found or all the responses you found after killing each of the sources in the circuit. That will be the total response of that circuit. In this example, how many sources do we have? You can see we have 1, 2, 3 sources. There are 3 sources in this particular analysis or illustration. 2 voltage sources and then 1 current source. Okay, so when you kill a voltage source, that would translate to you short-circuiting that particular circuit, okay, or that particular terminal or that particular branch where the source is. When you kill a current source, it leads to you opening that particular circuit of the branch where that current source is located. Killing a current source is connected to opening the circuit. Killing a voltage source is connected to short-circuiting the circuit. You know that already. So we talked about that when we're talking about Thevenin equivalent and Norton equivalent and a couple of other topics we've talked about before now. So we're just going to apply some of those principles here. We are supposed to kill all the sources except one. So we are killing the 2 voltage sources first. We kill this one, and then you can see the voltage sources 1 and 3 are gone, and then we have short circuit there, leaving only current source alive. And then we go ahead and analyze this circuit based on just that current source that is alive. When that happens, you restore the sources that you have killed, and then you keep only one more source alive. If we restore the sources killed, and then we kill the current source, we kill this current source now and then kill this voltage source. The only source alive will be this Vs. So in this particular case, what we are doing is keeping just this voltage source alive, and then we're killing these 2. And then once that is done, you get a response from this circuit, you document it as an equation and keep it somewhere. The next thing you do is to look for the other source we have not killed. So far, we have killed this before, we have killed this before, we made these alive. We have killed this and we have killed this. We made this alive. This voltage is alive. Now we are going to kill this, okay, and then kill this and then make this voltage source alive. All right. So when you do that, you get a third equation after analyzing this circuit. And now we would have 3 major equations on our ends. 3 major equations on our ends that we can work with to find the exact response to the circuit. So in many cases, that simply means here you're going to have I1A, I1B, I1C, I2A, I2B, I2C, B, VSA, VSB, VSC. Okay, you're going to have all of those in all of those 3 equations, and as many of those A's and B's that you can have for all the currents and sources that we have in the circuit. Those are the things you're going to have. And with that, you will be able to analyze the circuit completely at the end of the day. Now, to make it easier, we're going to look at 1 or 2 examples together, and then we'll look at how that applies. Here is an arbitrary example that we can quickly look at. An arbitrary example: find the current I2 flowing in resistance R2 in the following circuit by using the principle of superposition. So this is a circuit. We're looking for I2. This is I2, okay, flowing in the resistance R2. This is R2 in the following circuit. So kill the current source and solve the circuit. That's the first thing we're going to do. And when that is done, we'll replace the source we killed, and then you kill the voltage source, and then find the resulting circuit, and then, of course, the resulting equation. Whatever we obtain, we'll sum them together, and we'll get our total answer. So when we kill the current source, this is the current source. When you kill a current source, you open the circuit. So the circuit remains open at this particular point. This simply means that all the currents passing through R1 will just go straight to R2. Nothing will pass through this branch in the middle anymore because the circuit is open anyway. When this happens, it means that R1 and R2 are going to be in series. The equivalent resistance in the circuit will therefore be R1 plus R2. Okay, so to find IA in this case, our IA, now don't forget that this is I2. So this becomes I2A now. This is normally supposed to be I2A at the top, following by our notation. This is notation we're going to use going forward. So this is supposed to be I2A, by the way, but in this case, they just wrote IA. So let's assume our IA in this case is the same thing as I2A here. So let's assume both are the same now, okay? So our IA will therefore be equal to the voltage that we have on the circuit using Ohm's law, the voltage divided by the equivalent resistance in the circuit, R1 plus R2. This is going to be equation 1. You keep it somewhere. Equation 1, when we kill the current source. Then we can go ahead and kill the voltage source. When we kill the voltage source, we must replace the current source to the circuit. So we are replacing the current source now and killing the voltage source. This time around, what we are doing is to short circuit this branch because we are killing the voltage source. Okay, so we are going to have a short circuit here. In this particular case, what we are going to apply is current division, because the current passing through R1 is now different from the current passing through R2. They don't have the same current passing through them anymore. So now we want to find IB. IB again will be the same thing as you saying I2B. Okay, so IB and I2B are going to be the same. Okay, so for this example, we're using IB. So how do we find our IB? Our IB using current division, which we have already discussed in the previous lessons, will be equal to the I source, that's what we have here, multiplied by G2, because we are looking for I2B, so it has to be G2 here, multiplied by G2 divided by G1 plus G2. G represents conductance. Conductance is equal to inverse of resistance, that is 1 over R. So G would be equal to 1 over R. So if we have our R2 here, G2 will be equal to 1 over R2. For R1, G1 would be equal to 1 over R1. So you have all your values, substitute them right in here, and you have your IB. So your total is now going to be I2 will be equal to IA plus IB. Or if we use the notation we are going to adopt going forward, I2 would be equal to I2A plus I2B. Okay, so these two mean the same thing. These two, they are equivalent. Okay, they are the same, they mean the same thing. So you should be able to use this new notation to avoid confusion as we move on. All right. We have an example that we should handle together. Example, solve for the circuit variables I1 and I2 by applying the principle of superposition to the two sources. So we have voltage source, this is first source, we have current source, the second source. This is I1, and then this is I2. So we are looking for I1 and I2, and we have been asked to use superposition method to solve this problem. Okay, to do that, we are going to have to kill one of the sources, and once we do that, this is what it will look like. Let's assume that we are killing the current source first. Kill the current source to solve for component A. When you kill the current source, we are going to open this circuit. When you open this circuit, this is what it's going to look like. Nothing is going to be happening here. All right. So all the currents, okay, are going to be moving this way. That simply means that these guys are now going to be in series because all the currents are just the same current passing through them, all things being equal. So in this particular case, the equivalent resistance would be equal to 2 plus 4 since they're in series, and that will be equal to 6. The voltage in the circuit, effective voltage in the circuit is 6 volts. Using Ohm's law, your I1A, we want to find this current moving through these 4 ohms. Okay, I1A would be equal to 6 volts divided by 2 ohms plus 4 ohms. And that will be equal to 1 ampere. Okay, and if you apply KCL to this particular point here, KCL tells us that all the current passing through a particular node, the summation of all the current around the node must be equal to 0. And when current is leaving a node, it is positive. When current is entering a node, it is negative. Okay, so current leaving the node here is I2A. Current leaving the node right below, going through 4 ohms, will be I1A. So this becomes plus I1A because those two currents are leaving, and then we do know when they are leaving it's positive, so it becomes I1A, right? So adding both of those currents together will give us 0. So if we know I1A to be 1 ampere, it means I2A will be negative of 1 ampere. I2A will be minus 1 ampere if this goes to the other side. All right, so our I2A will certainly be equal to minus 1 ampere. So we know I1A to be 1 ampere, we know I2A to be minus 1 ampere. And we got that by actually killing the current source. That's how we got that. The next thing we want to do right now is to restore the current source and then kill the voltage source. So kill the voltage source to solve for component B. If you do that, this is what you would have. When you restore this, you still have our 3 amperes back. We have our 3 amperes back as the current source, but this time around, this place is a short circuit because when you kill voltage sources, you replace them with a short circuit. All right. In this particular case, we now have I1B and I2B. How do you find I1B? I1B, we're going to apply current division. So I1B would be equal to the effective resistance in the circuit. Don't forget, we are saying this is supposed to be equal to G. If this is I1B, so it's going to be G1 divided by G1 plus G2. That's what it means. G1 plus G1 plus G2 multiplied by the current source, which is going to be 3 amperes. Okay, so that's what this means. Yeah. Our G1 in this case is going to be 4. If we are looking for I1B, okay? So our G1 in this particular case would be equal to 4, and our G2 would be equal to 2. If G1 is equal to 4, this becomes 1 over 4, all divided by 1 over 2 plus 1 over 4. This is what it's going to look like. Then you multiply everything by 3, okay? So 1 over 4 plus 1 over 2 right at the bottom is the same thing as 3 over 4. So this entire stuff here is 3 over 4, right? So this gives us 3 over 4. So you have, this is eventually becomes 3 over 4, okay? So you now have 1 over 4 times 4 over 3. Everything multiplied by 3. So if we have it that way, that simply means that we have 1 over 4, which is what we have right at the top here, divided by 3 over 4. When you invert it, it becomes multiplied by 4 over 3. That's just mathematics. And then multiplied by our current, which is 3 amperes. So this 4 cancels this 4. This 3 cancels this 3. And then our I1B that we are looking for, this I1B will therefore be equal to 1 ampere. Okay, becomes 1 amperes. So I1B automatically becomes 1 amperes. We use that to deal with this. Okay, so that's exactly what we do have here. I1B automatically becomes 1 amperes. All right. So if we go ahead, we need to find I2B now. Okay, we need to find I2B. How do we find I2B? This is going to be our I2B here. I think I'm noticing that this calculation, my calculation is what they should go by. They misplaced the arrangement here briefly, so don't allow that to deceive you. Just go straight using the calculation I used, okay? I1B is 1 ampere. You will notice that here they used 2 right at the top here. Okay. All right. So just follow my calculation. It will make life easier for you. Okay, let's go ahead and find our I2B. The I2B, therefore, would be equal to our source current, which is 3, then multiplied by 1 divided, that's going to be G2 now. Multiplied by G2. We said this is our G2, okay? So it will multiply by 1 over 2 divided by 3 over 4, all right? That's G1 plus G2. So if you rearrange that, this gives us 3 multiplied by 1 over 2 multiplied by 4 over 3, all right? So 2 here cancels and gives us 2 here, 3 cancels and cancels this. So you're left with 1 times 2, and this eventually gives us 2 amperes, as you can see here. So our I2B, which is what we do have here, would be equal to 2 amperes. You can see 2 amperes here, and for the first one, we got 1 ampere here. What we are looking for is not I1B or I1A or I2B or I2A. That's not the destination. What we are looking for is I1 and I2. Now that we have the A component and the B component of I1 and I2, we can then go ahead and just add them together, and that gives us the final answer using the superposition principle. Let's quickly check out and see what that looks like. So if we take it a step further, this is what we would have. Applying the superposition principle, which is the third step we should take now, that would give us I1 would therefore be I1A plus I1B. Notice that it is not I1A plus I2A, it is I1A plus I1B. What you have right at the bottom here remains the same. The only thing changing is A and B, representing the various components we have after killing the sources individually. Okay, and that will be 1 plus 1, that gives us 2 amperes for our I1, and then I2 will be I2A plus I2B, and that gives us 1 ampere at the end of the day. This is how to use superposition principle. This is a simple circuit, and easily we have been able to do this. There are times when you will be given more complex circuit, but what matters, the most important thing is to understand the procedure. Once you understand the procedure, the rest is very easy. Okay. Now, one important point I should make here before we go ahead, and we should look one example regarding that, is the fact that dependent sources are not killed when applying superposition principle. Okay. Also, we don't apply superposition to power. We only apply superposition to the components of power, such as the current and the voltages. So after we have obtained the current and obtained the voltages with the voltage, we then multiply the current and voltage together to obtain power. I think, okay, I just mentioned this now. Dependent sources are not killed when using the superposition method for calculating circuit parameters. I just explained this. And in linear circuits, power does not superpose since it is not a linear function of voltage and current. Power needs to be calculated last once the components are summed. This is important. Please pay attention to it. Okay. All right. Let's deal with this example together. This is the last example we are going to deal with together. Find the voltage V and the power dissipated by the 3 ohms resistor. When power is generated, it is equivalent to power being delivered. When power is dissipated, it is equivalent to power being consumed or absorbed. Okay, pay attention to that. So the first thing we want to do is to find our sources. How many sources do we have? We have 3 sources. We have the voltage source, we have the current source, and then we have the current dependent voltage source. Okay, so we have, this is a voltage source depending on current. So this is a current dependent voltage source. Since we have these, and we already mentioned that for dependent sources, we don't kill them. So this remains in the circuit. That simply means at some point we kill current source, find response from this circuit, find the response from the circuit, and then we restore the current source and kill the voltage source, find the second response, and then from there we'll come up with our final solution. So let's try to implement that right away. Kill the current source to solve for component A. When you kill the current source, this becomes an open circuit, okay? And then you have 1 ohms here, 3 ohms here. You have the voltage source here. You have your dependent source here. And then this is the V that we are actually looking for, by the way. So that V now becomes VA. Since we are dealing with component A, it becomes VA. I1 becomes I1A. I2 becomes I2A. In this case, we don't have I2 yet. Okay, so let's not bother ourselves with I2 yet. When we get there, I'm going to explain to you when to bother ourselves about it. Then 2I1 then becomes 2I1A also, okay, because we're dealing with component A. Let us apply KVL in this particular case. We have minus 12, right? Because we know that if we draw our path like this, we are traversing on negative here, so it becomes minus 12 if you remember our concept of KVL. And then we go, this becomes plus VA, right, isn't it? Plus VA right at the top here, plus VA. And then if we keep going down, this is the voltage source, by the way, then it becomes plus 2I1A, all right, because we're traversing from positive to negative. And then it continues with, if we go this way, this is 1 ohms. The current passing through this 1 ohms is I1A. It becomes plus I1A. As we mentioned earlier, you sum all the voltages in the loop together and equate them to 0. The sum of all those voltages must be equal to 0. If we have this, we can go ahead and quickly rearrange. If we want to write everything in terms of current, we can do that. What is our VA? Applying Ohm's law. We can find VA here. Our VA applying Ohm's law would be equal to IR, current times resistance. The resistance is 3. The current passing through it is the I1A. Okay, so you have I1. Let's use this circuit rather, because we have opened the circuit here. So the current coming from here comes here. It can't go straight. It comes straight down. So VA would be equal to 3 multiplied by 3IA. So if you put that here, you can replace this VA. If you do that, what you're going to have left is 2IA1 plus I1A gives us 3I1A. 3I1A plus another 3I1A, that should give us 6I1A. So what we have left is 6I1A to be equal to 12. Because this 12, we can take it to the opposite, to the other side, and then it becomes plus 12. If you replace these ones with 3I1A, it becomes 3I1A plus 2I1A plus I1A, and that is a 6I1A. Eventually, you end up with I1A equal to 2 amperes eventually. That's what you have at the end of the day, which is exactly what we do have right at the top here. I1A would be equal to 2 amperes, okay, for component A. And once we do that, we can easily find our VA. Okay, we said VA is equal to 3I1A. So 3 times 2 will give us 6. So our VA will therefore be equal to 6 volts, which is exactly what we also have right here. So we have I1A and then we have VA. And then we now go ahead and replace the current source we killed. We bring it back to life and kill the voltage source. If you do that, this is what would happen. Now kill the voltage source. The independent source only. Like we mentioned earlier, we cannot kill the dependent sources. So this source is alive. See, we can't kill it. Okay? If we do that, this is what we're going to have. If you kill the independent source of 12 volts, that means you're replacing it. It means you're replacing it with a short circuit. So we have a short circuit here. And then we are putting our current source back. Let's first of all take KCL around this particular node. If we take KCL around this node, we do know that current entering a node must be negative. Our notation, we talked about this much earlier in previous lessons. And we know that the summation of all currents around the particular node must be equal to 0, all right? So I1A, that's as we have it, I1B, we are replacing all currents and voltages with B now. So I1 becomes I1B, BB becomes B becomes BB, I1 becomes I1B. And since we now have different currents passing through the resistances, so the current passing through the resistance 3 ohms would be I2B, because I1B is not the current passing through this resistance. Now, we have another current coming from this angle. So when both of them meet here, the current passing through 3 ohms resistance will have its own unique current. You can label that I2B, okay? Which we didn't talk about in the first component, component A, but we're talking about it now. So we have I1B is entering this terminal, this node, so it becomes negative. I2B is leaving that terminal, it becomes plus I2B, isn't it? And then which other current is coming to this node? 6 is coming to this node. 6 is also entering that terminal. Is that going to be negative or positive? 6 is entering that terminal too. It will be negative. So minus 6 would be equal to 0. Okay. So from here, you can say our I2B is equal to I1B plus 6, which is exactly what we have here. Okay, that's how we got there by applying KCL. We can then take KVL. Okay, since we already have one equation, we can then apply KVL. If we do apply KVL, we would have, let's apply KVL to this loop here. If we apply KVL, it simply means we have 1 times I1B becomes I1B times 1, that's I1B, okay, plus VB, all right? VB would certainly be equal to 3I2B, so it becomes plus 3I2B. We have quoted the precedence for that, plus 2I1B is what we're going to have next, 2I1B. So it looks like we have handled all the parameters in this path or loop. Everything according to KVL must be equal to 0. Okay, that's what we do have. But we do know that our I2B is I1B plus 6. So you replace this I2B with I1B plus 6. If you do that, this is what you're going to have. I1B plus 3, I1B plus 6 plus 2 I1B equal to 0. If you rearrange, you can then find your I1B to be equal to minus 3 amperes. Okay, so from what you can see, we have our I1A to be 2 amperes, I1B to be minus 3 amperes. This makes it very easy to find I1. So this I1 we have here, we can now find it very easily by just saying I1A plus I1B, which will give us our I1. Now, applying Ohm's law, our VB is equal to 6 plus I1B, and that will give us 9 volts. We know that our VB, like we mentioned earlier, is equal to 3I2B, right? And then we said our I2B is I1B plus 6, which is exactly what we have here. So our VB will be equal to 3 multiplied by I2B, which is this, and that gives us 9 volts. We are looking for the power. So since we know the resistance attached to this V, and we know this V, it becomes very easy to find the power. If we know resistance and we know voltage, the easiest formula to use to find power would be equal to V squared over R. That would be the easiest formula to use to find power. Okay, now before we find power, now this is one of the mistakes I have actually explained that we cannot afford to make, and that is assuming that our V is VB. Okay, So what we have now is 9 volts for VB. We have VA to be 6 volts. So our total V will be equal to VA plus VB, and that will give us 15 volts. Now that we have 15 volts, we can then go ahead and find our power, which is now going to be equal to V squared over R, and that's 15 squared over 3, and that gives us 75 volts. Okay, this is very important for us. So the power dissipated by the 3 ohms resistor will be equal to 75 volts. One important point I would like to mention here is that you have to note that superposition component of components A and B powers does not give the right answer. You can try to superimpose for power, okay, and say you want to superimpose, find PA and then find PB and then add PA and PB together. It doesn't work that way. That's not how it works, okay? So this is where we are going to stop today. This is the last example I'm going to give to you guys.